have a vault as our conference room, as this used to be a gold mine. We kept the maps to the gold in this vault behind me. Now, we've transformed the facility into a laboratory for underground science. Understanding how the universe works is really the ultimate goal. Understanding properties of neutrinos is extremely important. It can help answer questions about why we exist, why there is more matter in the universe than antimatter.
Majorana is an astrophysics experiment, and what they're trying to do is study properties of neutrinos.
I'm getting ready to go down the elevator, and we're getting our mine-ready equipment, steel-toed boots, coveralls, personal rescue device in case of an emergency, and trusty headlamp.
I used to work in a mine in Utah, and I used to go down by myself. You know, it was before all the safety regulations that we have.
Discovering dark matter would be tremendously exciting. We have no idea what dark matter particles are. We've never seen them. We know they exist. The evolution of galaxies, gravitational lensing, there's lots of indirect evidence, but we have no direct evidence of dark matter particles interacting with our known universe.
My focus is trying to use the Majorana detector to detect dark matter. We might not do as well as Lux, but you know, it's a different kind of experiment. We're using germanium instead of xenon.
It's interesting because neutrino is the most abundant particle in the universe, and so you'd think we know a lot about it. But it turns out we don't, because they're very hard to detect because they only interact through the weak interaction. This neutrinoless double beta decay is the only way to measure the true nature of a neutrino, and there's a possibility that the neutrino is its own antiparticle. Why do we have more matter than antimatter in the universe? The Big Bang created equal amounts of both, but yet we exist and we're made of matter. And our experiments are designed to measure very precisely the energy of those two electrons and to see if more often than not you get all the electrons taking all the energy. Beta decay is just simply an atom decaying into another atom emitting an electron. So we're really trying to understand how do we even exist. Some people will call us low energy physicists or nuclear physicists. We're trying to look for also new particles or understand detailed properties of particles without creating them, but more by trying to observe them and look for very rare processes to happen. That's why we're so deep underground.
I am the Davis campus custodian.
Okay.
So I work with both experiments and keep everything clean as much as I can, one day at a time.
Things are a little awkward. Forefront of science.
You have to put it on and step on the mat.
Okay.
This is our glove box. For obvious reasons is the name. The reason we have this glove box is to maintain a very, very clean environment of the inner detectors that we work on.
I think the most exciting thing is, like any basic science, this is the first time that it's been done. We are growing the purest copper in the world for the Majorana Demonstrator, which is being used as the structural material for parts, holding detectors, everything down to a high voltage pin, and then as large as shield plates to isolate the detectors from any background noise that could disturb them. We have quite a few scientists here on site. We really have the miners that are support crews preparing the environment down there for our lab spaces or helping us with just day-to-day activities of movement of equipment or material.
Science doesn't necessarily have a human time scale, okay? So it's been at least 30 years that we've been doing these underground experiments.
I work with the Majorana experiment. My main work at the 4850 is help with the construction of the experiment itself, building the detector, the heart and soul of the experiment.
I've been here for 4 years. I'm the radiation experiment health and safety manager.
Okay.
So my job is to take a look at the research that's going on here and making sure that much as possible, it's being done safely.
When you say neutrinoless double beta decay 3 times as fast as possible.
Neutrinoless double beta decay, neutrinoless double beta decay, neutrinoless double beta decay.
Good job. I think that's the record.
I have to say it a lot.
Yeah. To build a bigger detector, a more powerful detector, and still get 0 results, what does that mean for physics?
So it just turns out the physicists were smart in how they built the model. There's a possibility that you have to build an infinitely big experiment to detect it, so it keeps us working.
Very clever. If we can understand these things, we might be able to shed light on advances in Higgs boson fields, string theory, and even draw light into the grand unification of quantum mechanics and general relativity.